We are in S domain, and what would be changes time domain circuit theory if we transfer this theory to S domain has been examined on this frame. And then we said we could use serial parallel connections in order to do the analysis in S domain. There are some benefits of using the serial parallel connection S domain if you compare it to time domain. We examined it already. Now we will be examining this frame now, which is source transformation. So we're going to show you that source transformation is a useful tool to be used in S domain analysis. The first we're going to examine in general what the source transformation is. We have done the similar things in time domain and frequency domain, so we are repeating here what we have done already. And in this source transformation, so we can compare source transformation in different domains. In time domain, we have done the source transformation for only the resistive circuits. That means dependent source included, resistors included circuits. L and C elements included circuits in time domain is not good for the source transformation analysis. But in here, in frequency domain and S domain, we could use the source transformation for those circuits which has got inductor and capacitor in it. So that is the advantage of being in frequency and S domain in terms of source transformation. So we're going to examine the source transformation in general first, and then we will be applying this source transformation usage in circuit analysis in S domain. The circuit the example circuit we are going to use here is the same as the previously used circuit for serial parallel connection example. So conclusion is this: the same circuit will be examined in source transformation usage way, will be analyzed by using the source transformation, and also already been analyzed by using serial parallel connection. Let's move to open board now. Open board. So this is in Turkish, but I will write it in English right here. Source transformation. So what we are saying, if there is a independent voltage source connected in serial with an impedance, can be replaced with an independent current source in parallel with an impedance. So in order to see that equivalency, what we are saying is this. So this is a circuit, a load connected to it, and left-hand side circuit ZL load and right-hand side circuit ZL load. Current and voltages do not change if we replace this independent voltage source in serial with an impedance here with an independent current source in parallel with an impedance. How we are going to prove it? It is easy. Left hand side, the voltage here, V load, is equal, these two is connected in serial, so Vs over Zs plus Zl gives you that current. So I am saying this. So this ratio gives me that current, isn't it? If you multiply that current with ZL, I am going to get V load. So that's V load, left hand side. I am moving now to the right hand side, saying now this ZS and ZL are connected in parallel, so equivalent Z is ZS times ZL over Z, made a mistake, ZS plus ZL. So this impedance, so that's the impedance here. So this impedance multiplied with IS gives me V load prime. So this is what is here. So we are saying these two equivalent. If these two blue marked circuit here is equivalent this blue marked circuit, then if they are equivalent, then ZL voltage and ZL current do not change on the left hand side and the right hand side. So in order to have that V load equal to V load prime, what we see here, this ZL over ZS plus ZL is common here, isn't it? What is left is VS here and this here. So conclusion is this, if VS is ZS times IS, then V prime load is equal V load. So in order to have those two circuits equivalent, this should be true. So conclusion is simple. If you've got that connection on the left hand side, if I replace this with this independent current source and an impedance in parallel, which is the same value of the serial impedance, then IS value must be equal to VS over ZS. That means if I select this independent current source current is equal to left hand side VS over ZS, then my voltage on that ZL and on that ZL prime is going to be the same. So no change if I do this transformation. So you could do the similar thing for the current as well. You're going to end up with the same result. So in order to have this current equal to this one, that relation must be correct. So that means that relation must be correct. And that relation tells me what the source transformation should be. You can say that on the other hand, you can say that if you have a circuit like that, and this current source is in parallel with an impedance here like that, so you can replace this one with that blue one, blue marked here, or I am marking it now with green. So if you do that transformation, we're going to use this ZIS is available on the right hand side. To move it to VS, we've got to multiply ZS with IS in order to get the VS value of the left hand side independent voltage source. So that means you can go from left to right and similarly from right to left. If you do it that direction, you're going to calculate IS in terms of VS and ZS like this. If you are moving from right hand side to the left hand side, so you're going to put independent voltage source voltage is equal RS ZS times IS, which is available here. So this transformation can be used in circuit analysis, that we are going to see it on an example. Just remind you one thing. Clear all this is a bit confusing, so clear all this. So if you look at the right hand side and left hand side circuits here, the number of nodes on the left hand side is 3, isn't it? And right hand side the number of nodes is just 2. So one node disappeared. What does this mean? If a circuit given to you, consider that ZL represents many of the elements included circuit. And then you are analyzing this circuit by using the node voltage method. Now this conclusion tells me now, if I do the source transformation, I reduce the number of node equations by 1, isn't it? So you can write one less equation if you do the source transformation from left hand side to the right hand side. That is a benefit. The other thing that we could say, if the number of meshes here is just 2, isn't it? But in here it is just 1. So you might consider ZL many elements included circuit. So that means if you move from the right hand side to the left hand side, the mesh equations, the number of mesh equations are going to be reduced by 1. So 2 mesh replaced with 1 mesh. Therefore you're going to write 1 mesh equation less if you do the source transformation from this to this. So how we are going to use it in a circuit? Let's move to the next step. Here you are. This time domain circuit has been examined for serial parallel connection example previously. So this is the S domain circuit corresponding to this given here. Now what we are saying here, we will be doing now source transformation for the analysis of this circuit. How we are going to do it? See that green area here, there is an independent voltage source in serial with a resistor here, 10 ohm. So you can replace those two by using the source transformation with that green here. How we are going to do it? So this independent current source, just remind you one thing, I just missed that. While we are doing the source transformation from the independent voltage source to independent current source, pay attention to these references. So according to passive sign convention, the current of these independent voltage sources is downwards, but this current of the independent current source here is upwards. So you could use the source transformation by paying attention to that references that has been taken into account here. Replace this green shaded circuit with that green shaded circuit, which includes the independent current source of which current is upwards, like that here. So how we are going to calculate this independent current source current is simple, isn't it? This voltage over 10. So this independent, that IS is that Vs 10 over S oh 10S, oh my made a mistake, sorry, 10S over so that is Vs. Vs divided by 10 gives me that Is. So this is So if you do the calculation here, you're going to end up with this. So this impedance is the same impedance. So we replaced this green with that green. In this case, this 10 ohm and 20 ohm becomes in parallels in that blue area. If you replace this blue area with this equivalent, we already know that. So that is going to be 20 times 10 over 20 plus 10. So that is the resistor, equivalent resistor resistance value. So independent current source connected with a resistor. So that pink one. The pink area, if you apply the source transformation once more, transfer this independent current source to independent voltage source. So forget this, okay, how I'm going to do it. So this is left from something else, you see, forget that. So this pink one is going to be replaced with this pink by using the current source transformation to voltage source transformation. How are we going to do that transformation? This voltage source voltage is going to be this IS times that resistance, isn't it? 20 over T. So if you do this operation, you're going to end up with this. This impedance or this resistor value is going to be the same when you move it from parallel to serial. So at that stage, what we see here, three elements are connected in serial, isn't it? So summation of those two, that means 20 over 3 plus 0.1 s plus 10 to the power 4 over s. That is this resistance. If I divide this voltage to that resistance, that voltage is 20s over 3 times s squared 10 to the power 4. That gives me that current. So okay, we found a current. How we are going to get benefit out of this? So we are saying if you do the equivalence operation in step by step, in your original circuit, if there are some elements in your original circuit or your final circuit, that's our final circuit, and that's the original circuit. So this inductor and a capacitor, those two are common in the original circuit and my final circuit. The others are not common, isn't it? For example, these elements are not seen here, and those two are not seen in the original. But these two seen in both of them. Because of that, the operations that we have done is the equivalent circuit operations. Those common elements, current and voltages, whether you are in this circuit or this circuit, do not change because of the equivalent circuit concept. Then I am saying this inductor current here is this current, isn't it? So that current is IC. That IC is also that IC. So that means by just one operation I found this after 2 or 3 source transformation, and this current is equal to my original circuit capacitor current as well. Then I am saying I can calculate all the elements current and voltages, because this current multiplied with this impedance give me this element voltage. So I found this element current and voltage. I know this capacitor is connected in serial with that inductor. So this current is equal to this inductor current. So I found the inductor current, multiply that current with the impedance, you get the voltage of this inductor. So I found both current and voltage of those two elements. So how I'm going to find this element current? Voltage first. I already found the voltage of this 2, so summation of those two voltage gives me the voltage of this element. So I found the voltage of 20 ohm, divided by 20, you get the current of this element. So you know this current, you know this current, summation of those two current gives you this current. So you know this element current multiply 10 gives you this element voltage. This element current I know with the difference of sign is the same as this independent voltage source current. So I calculate all the elements current and voltages by using this source transformation analysis technique. So that's a good example for you to see the benefit of source transformation in S-domain analysis. And you can compare this result with the serial parallel connection result, because in here we have chosen the same circuit for the analysis. So that's the end of this video then.